Solve this differentiability problem or die.
Okay, well, I haven't learned this for a while, but thinking back, I know that differentiability is associated with continuity. And I know that a function is continuous at a point if it meets three requirements, those being the limit as x approaches a equals f of a, and f of a must exist, and the limit as x approaches a from the left of f of x equals the limit as f of x as x approaches a from the right of f of x. So all points on the function are continuous except the jump discontinuity at x equals 4. From what I can remember, when a function isn't continuous, it isn't differentiable either. So it seems that the rest of the function is continuous, and I can tell by using the trick of never letting your pen leave the paper. Therefore, I believe that f of x is not differentiable at x equals -4.
Incorrect. Now die.
Thank God I lost him. That was really scary. I'm never going back there again. Oh my God.
Here is your second pass.
Okay, well, clearly we did something wrong last time. Now we have what seems to be an absolute value graph. And it's continuous for all of x. Well, that's not good. If it's always continuous, how can it not be differentiable somewhere? Let's think a little deeper. We are trying to find a point that cannot be derived, or in the case of a graph, a tangent line that cannot be drawn. So let's try drawing some tangents. See, from the left of the vertex, they seem to be negative, whereas from the right, they're positive. So how do we know what the tangent of the vertex is? That's just it. We don't know. Therefore, f of x isn't differentiable at the vertex when x equals -1. So it seems that if there's a corner on a graph and the tangents from the left and the right side of the corner are different, it's not differentiable. Oh my God.
Solve this math problem.
Alright, now that we know how to use tangents to find points where the graph is not differentiable, we see there's a corner or a change in the slopes at x equals 1. That's a start, but now we need to do it algebraically. Let's first start by writing the equation of this piecewise function. So we can see that when f of x is less than 1, it's the function x. And when it's greater than 1, it's a negative quadratic. So we'll start negative quantity x minus 1, it shifted the right one, squared, plus 1, shifted up. Okay, below we'll write that in more proper piecewise function notation. So x when x is less than or equal to 1, and negative quantity x minus 1 squared plus 1 when x is greater than 1. Alright, to reassure that we know that it's not differentiable, we're going to draw in some tangents. So we see that it seems to be 1 from the left and maybe 0 from the right. It's the vertex. Alright, so thinking back to one of the continuity rules that states that the limit as x approaches a from the left of f of x is equal to the limit as x approaches a to the right of f of x, we can substitute in f prime of x for f of x, essentially. So writing that down, we have that rule. And if we remember back to derivatives, we know that f prime of x is just equal to f of x minus f of a over x minus a. And a is a constant. Okay, so plugging that in algebraically, we can prove that f of x isn't differentiable at x equals 1. Let's start out from the left and begin plugging things in. It simplifies, so we're going to start with x, because that's the function f of x from the left, minus the value 1, because that's f of 1, over x minus 1. That'll cross out, and we're left with the limit as x approaches 1 from the left of f prime of x is equal to 1. We're going to do the same thing for the right here, so we're going to do limit as x approaches 1 from the right, f of x, which we're using the quadratic equation, so negative quantity x minus 1 squared plus 1. Then we're going to plug in the value a, which is 1. So when we plug that in, we're going to get 0 for that's all going to cancel out right there, and plus 1, so we're left with 1 over x minus 1. So the 1 and the negative 1 will cancel, and then we're left with the numerator, and that's actually a factorable term. So both factors are on the top and bottom, so we can cross out the denominator, and we're going to be left with negative x minus 1. So then we're going to take the 1 from the limit and plug it in for x, and we're going to be left with 0. So that means that the slope of the tangent from the left is 1, whereas from the right it's 0. So using that information, we know that it is not differentiable at x equals 1.
Good job. Go to the house for your final task.
I am Zeldor, Destroyer of Worlds. Here's your final task. Succeed, or actually that is time.
Alright, so the final task is asking us to formally define when a point is not differentiable. And using all I've discovered, we can conclude that a point is not differentiable when it is either not continuous, which can be verified with the 3 rules of continuity, which we discussed earlier in the video, if you'd like to scroll back and find those. Or B, that the limit as x approaches a from the left of f prime of x is not equal to the limit as x approaches a from the right of f prime of x.